get out of the problem here and get into this.
What was the unit again?
It's going to be radians per second squared. Okay, so that's, I mean, that's what it's an acceleration unit, right? Per second squared.
Yeah. I mean, so the fish acceleration are exactly the same.
Yeah. They are what they are. They're both accelerations, just different kinds of acceleration.
That's why it's different.
Yeah. All right. We talked about that things rotate, but certain things, like the wheel on Wheel of Fortune, actually change how fast they rotate, right? It actually stops spinning. But at the beginning, to get the wheel on Wheel of Fortune to go, or the big wheel on Price is Right or whatever, right? We need to start that thing spinning. So first, let's go here, okay? Go to the bowling alley, and we roll the ball down the lane. It hits the pins. What happens to the pins?
Striking.
Okay. So first, do they start moving?
Falling.
Well,
Smacking
okay. Actually, they actually start doing a couple of things, right? They'll start moving backwards or sideways, depending on how the ball hits and how the other pins hit them, et cetera, et cetera, et cetera. But if we take a look at like this one here, right? What else are they doing? They're moving backwards, but they're also what? They're also spinning. They're also rotating, right? So we can have two types of motion occurring at the same time. Here, this is like a stop, capture, whatever picture of a hammer being thrown through the air. Okay? Notice here's like the beginning picture right there. Okay.
Yeah, how is it spinning?
Hammer. Right? There's the handle. There's the. Okay. Anyway, here's a hammer going through the air. I don't recommend that you throw a hammer through the air, but you know. Okay. Anyway, but you can see here that this object is both rotating and moving. Right? What kind of path is it moving on? If we look at this red dot, what kind of path is it taking? It is a J, yes. Okay. It's a what? It's an upside-down parabola, right? Because as it's flying through the air, what is it? It's a projectile, right? So it follows that projectile path, even as it's spinning. We would say in this case that these pins, the bowling pins from the previous screen, or the ladder in this picture, have both translational motion and rotational motion. Translational motion is something moving through space. If we go back to the example that we used the other day, we talked about the Earth moving in its orbit versus the Earth spinning on its axis to create night and day. The Earth moving in its orbit around the sun, that's translational motion, movement through space. But it also rotates on an axis, right? It spins around some axis as it's moving through space. Okay? So we can have both of these things occurring simultaneously. We just have to handle them differently. We have to describe them differently, even though they're occurring at the same time. Okay? Good here? All right. Let's go. I'm going to skip a couple of slides here. I'm going to go right here. All right. So let's go here. Okay. So torque. We talked about.
I'm just laughing. Like you're really excited.
Torque is fun.
It's in the movie, it sucked.
The movie may have sucked, but the word is fun to say. So we talked about that these three things correspond to translational concepts. Displacement talks about how far did we go. Velocity talks about what are we doing now. Acceleration talks about how are we changing, right? But torque also relates to something that we've spent a lot of time talking about. As far as the definition for torque, torque causes changes in rotational motion, or it causes angular acceleration. What does that sound a lot like that we've spent a lot of time talking about this year? That sounds a lot like force, right? Force causes acceleration, right? So this is the cause of angular acceleration. We sometimes refer to torque as the rotational equivalent of force. Just like we have rotational velocity being the rotational equivalent, or angular velocity being the rotational equivalent of velocity, torque being the rotational equivalent of force.
Did you just call it rotational?
I suppose you can, although you'll never see it printed that way like in a book. Because what we'll see is that torque will depend on force, but not solely. There's other things that will affect the torque of something. Okay? For example, children. Okay? Do you see the little tape marks there?
I see too.
Okay. So put your finger at tape mark A and spin the wheel. Okay?
All right.
Put your finger at tape mark B and spin the wheel. Okay? Put your finger all the way out on the edge and spin the wheel. Okay?
Yeah.
Okay. Easy, hard, rank them in order.
I think the outside was the easiest.
The outside was the easiest, okay?
The
And
inside is the hardest.
the inside is the hardest, okay? So we're seeing here, did you apply a force to that bike wheel?
Yeah.
Yeah, you did. But depending on where you applied that force,
How much torque it was?
that was how much torque it was, right? You caused a different change in the rotational motion of that object based not only on what you did to it, applied a force, but also where you applied that force, right? Does that make sense? So torque is going to depend on two things. It's going to depend on the force that we apply, and it's going to depend on the distance from the center of rotation. Okay. All right. So torque depends on the force that we apply to that object, but also the distance from the center of rotation. For example, here is our formula for torque. First, we use another Greek letter. Do Greek letter time. This is a lowercase tau.
It only has a part.
Tau, omega. What's the W?
Omega is the W.
Beta.
Beta. Alpha, beta, gamma, delta. Beta. Yeah, I can remember. At one time I studied Greek letter.
I never understood like how they had an alphabet, but they obviously didn't say alpha tau.
Like what?
Like they didn't say, you know, how to like our alphabet obviously.
Yeah.
You know, A, B, C.
Right.
We used that, but they didn't say, you know, alpha tau, epsilon or whatever.
Like for what? No, they made words out.
Well, yeah.
Like we make words out of ours.
I'm saying I don't think you can make Greek words up. Very little.
All right. Anyway, regardless.
It's really limited.
They actually have 24 letters.
I'm saying that it's on.
What? Yeah.
They say 26.
Oh,
24 ET1.
all right. We use tau to represent torque. A lot of times when you're writing tau, you can write it kind of fancy with the curvy top on it like this, or a lot of times you can just write it with a straight top like that, whatever.
It's like a J, you know, backwards J.
It does kind of look like a backwards J.
But
This is actually lowercase tau, right?
Is gamma
So there's a-
Y one?
Gamma is Y.
wait, so there's an uppercase tau?
Yeah.
Good afternoon. My name is Richard. Quick announcements.
This is gamma.
First, the JV bus will leave Westlake High School at 4
Uppercase
p.m. for Rocky River. I would assume that is softball.
It's a little different.
The varsity bus will leave Westlake High School at 5 p.m. for Rocky
No, I
River.
meant like,
So,
like,
softball,
Oh, yeah, it's like
softball,
lowercase
JV
r.
bus, and
It's like
varsity
our
bus
lowercase
for
r.
Rocky JV
some more
green
torque,
softball
is
game
that
has
less
been
force
canceled
or
today,
more force?
and JV tennis will start at 4 p.m.
That's gonna be-
Reminder, boys track and field have a meeting right after school in room 201. Now the announcement everyone's been waiting for, our winner in the question of the day. What is Mr. Davies' middle name? His middle name is Walker.
We already know that.
Winners today are Haley Smith, Rishma already, and Rhonda Hamden. Congratulations. Stop by the media center for your prize.
Yeah, I didn't know that you can
No,
enter
it
it.
was good.
See you tomorrow.
Where do you enter it?
Mr. Davies.
All right.
Oh, for
Yeah,
time.
yeah.
It's fine. Yeah.
Oh, yeah.
So you notice all the stuff in the hallway?
I love it.
All right. As far as torque is concerned, A couple of things affect the torque. First, the force will be actually applied. Second, this letter D, which we refer to as the lever arm. That's the distance from the center of rotation to where the force
Sorry,
is
everybody, a
applied.
quick correction. Those bus departure times were for lacrosse, not softball. I apologize for that. Lacrosse, 4 o'clock JV, 5 o'clock varsity. Thank you.
Yeah, Lancers.
So, force, F stands for force, D stands for lever arm. Lever arm is the distance from the center of rotation to where that force is applied. When we're talking about something solid, generally that D is just going to be what? Whoa. So, when we're talking about a solid object, generally that D value is just going to be the radius of that object. Okay? When you have something that's not solid, like the bike wheel, then we can change where we apply that force, just like I had Sheldon do there. Okay? Then theta is going to be the angle between the applied force and the lever arm, which means if we're going to start throwing in like thetas and sines and stuff, this torque probably has something to do with what? Component vectors, and we'll get into that a little bit more.